Today I am going to talk on derivation of ABCD parameters for the short transmission line. Before going into detail of the derivation of ABCD parameters of the short transmission line, just have a recap on the classification of the transmission line. I already give this classification that transmission lines can be classified as short line, medium line and long line. The basic criteria for this classification is the line length. The lines with less than 80 kilometers are classified as a short transmission line. The range of 80 kilometers, greater than 80 kilometers and less than 200 kilometers is classified as a medium transmission line. And the lines with greater than 200 kilometers are classified as a long transmission line. Another major thing criteria for this classification is that consideration of the shunt capacitance. In case of a short transmission line, the voltage levels are low, and that's why we do not consider the effect of the shunt capacitance. But in case of the medium and long lines, the voltage levels are quite high, greater than 132 kV. In that case, we cannot neglect the effect of the shunt capacitance, and that's why we will consider the effect of shunt capacitance in both the cases, medium as well as the long line. In these lectures, I will cover ABCD parameter derivations for the medium line and how to draw the phasor diagrams for this medium transmission line. That is the objective of this lecture. Again, medium transmission lines are classified in the three categories, or we can say that this medium transmission line can be represented in three ways. These three ways are N condenser model, the pi model and T model. These three models are derived based on the way in which we consider the effect of shunt capacitance of the line. In case of the N condenser model, we consider the effect of shunt capacitance at the end of a line. Whereas in pi model and T model, the way in which the shunt capacitance are considered are different. In the subsequent slide, I will discuss that how the shunt capacitance can be calculated or can be considered in pi and T model. So let us start with the first category of medium transmission line, that is condenser model. Before discussing this derivation of the ABCD parameter for medium transmission line with N condenser model, let us take one simple example. Let us say we have one line of 250 km long and the voltage rating of this line is 132 kV. Balance load of 225 MVA at the power factor of 0.8 lagging is connected at the receiving end with a voltage of 132 kV. The line, we know that three-phase line, three line conductors are there, and these three line conductors are spaced equilaterally 3 meters apart, and the configuration is somewhat like these three conductors are placed at the three vertices of the triangle, so the distance between all these conductors are same. Resistance of the conductor is 0.11 ohm per kilometer, and therefore the total resistance of the line, just get it multiplied by the length of the line, that is 250 kilometers. So we will arrive at 27.5 ohms. This 27.5 ohms is nothing but the total resistance of the line of 250 kilometer. The radius of the conductors for these three phases, each phase radius of the conductor is 0.8 centimeter. The radius of the conductor is 0.8 centimeter. So with these parameters, with this given data, we can find out the inductance of the line as well as the capacitance of the line. So you need to recall the equation of the inductance of the line. The equation of the inductance of the three-phase line is given by 0.461 into log d upon r dash. Just look at the r dash. You know that r dash is the effective radius of the conductor, and it is given by 0.7788 into r. Don't forget to put this multiplication factor of 0.7788. It is effective radius, and you need to consider, don't consider 0.8 centimeter, you need to consider 0.7788 into r. So based on that, you get the value of the inductance. This value will be in terms of the millihenry per kilometer, and this millihenry per kilometer if you want to find out this inductance, from this inductance you can find out the inductive reactance per kilometer, that with the use of the equations 2 pi fl. So you will get inductive reactance of 0.3896 ohms per kilometer, and from this if you multiply it by the 250, then you will get the total inductive reactance of this transmission line, medium transmission line. So you arrive at this value XL. From this you can find out the total series impedance of the line. The equation of the impedance is nothing but R plus jXL. You just put it. Value of the R is 27.5, XL is 97.4. You get the, in polar form, total series impedance is equal to 101.2 with an angle of 74.2 degree. This is a series impedance of medium transmission line. From that, so one parameter, already series parameter you have calculated. The second parameter is the capacitance. Capacitance per kilometer equation is 0.0242 divided by log D upon R. Just observe the difference in capacitance equation and inductance equation. In inductance equation it is R dash, whereas in capacitance equation it is simply R. So don't make mistake here to calculate the inductance. Don't make a mistake to consider the value of R while calculating the inductance and the capacitance. Based on that, you get the value of the total capacitance of the line is equal to 2.35 microfarad. From this you can calculate the shunt admittance by using the equation J2 pi Fc, so that you get the value of shunt admittance is equal to 7.38 into 10 raised to minus 4, angle is 90 degree. This is the summary of the parameters for the transmission line which is under considerations at present. R is 27.5, XL 97.4. From that you can calculate series impedance, and shunt admittance is already calculated. Now we will discuss first the medium line representation, that type 1, that end condenser method that we will discuss. Your first task from this slide is to identify the parameters used in these configurations. So first let us try to identify the first all these components or the parameters in this circuit or network. This is the first element is series impedance, that is series impedance is given by R plus jXL. We already calculated this value. R plus jXL has already been calculated. Another element, that is shunt admittance, Y is equal to J 2 pi Fc, that is already calculated. These two elements are already calculated. The third element is a load impedance. Load impedance is represented by ZL, and this load is connected at the receiving end, and voltage across those load impedance is VR, that is receiving end voltage. Try to observe in this case the ZL and Y. The ZL, that load impedance, and shunt admittance are in parallel. That's why we call it as a end condenser method. End condenser method, that means the shunt admittance is considered at the end of a line, so that load impedance and shunt admittance of the line are considered to be connected in parallel, and voltage applied across the load impedance ZL and shunt admittance is called VR. This line, now we excited this line, we energize this line with the voltage Vs. When we energize this line with sending end voltage Vs, this line will carry current. That current is called Is, that is sending end current Is. This sending end current flows through the entire series impedance of the line, and you know that this series impedance Z is equal to R plus jXL represents this entire 250 kilometer line. So this current, sending end current Is, flows through this entire 250 kilometer line, and that 250 kilometer line series impedance is represented by this Z is equal to R plus jXL. So this current Is flows through entire 250 kilometer and it reaches to receiving end. At this receiving end, there are two parallel connections. One parallel connection is load impedance and another parallel element is shunt admittance. So that this current IS is divided into two currents. One current, it is a receiving end current, and second current is a flowing through that shunt admittance. We call this current as a charging current. Again I am repeating, this sending end current which flows through the entire 250 km series impedance, it reaches to receiving end. At receiving end, shunt admittance and load impedance are connected in parallel, so that this sending end current IS is divided into two currents. One current will go to the load impedance, that we call it as a receiving end current, and another current will be drawn by this shunt admittance, that is IC. So IS will be equal to, if I apply the KCL at this point, then IS is equal to IR plus IC. So with these discussions, we can now formulate the equations, that ABCD parameter equations. In the lecture of the short transmission line, I already said that ABCD parameters are required to relate the sending end quantities with receiving end quantities. At sending end, we will consider the voltage and current, that is Vs and Is, and at receiving end again we will consider voltage and current, that is VR and IR, and we want to relate this Vs and Is to VR and IR through this ABCD parameter. So what is our objective? Our objective is to formulate the equation of Vs and Is in terms of VR and IR. That is only the thing that you need to remember, and based on that you need to derive all these equations. So let us write the first expression. That first expression is 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 equal to IC plus IR. Can you see that? How can I write this expression? IS is equal to IC plus IR. This is my IS and this is my IC and this is my IR. Apply the KCL so that I can write the expression IC plus IR, correct? So second equation from this, IC is nothing but I can write the expression of current by using the relation I is equal to Y into V. So Y is already there, and voltage applied across this shunt capacitance is nothing but the voltage VR. So this IC is represented by Y into VR plus IR. So this is my equation number 1. Now I will write the expression of Vs. So Vs, you can know that this is my sending end voltage Vs, and the sending end voltage Vs is nothing but this is the, at this point voltage available is VR. So this is VR, and if I add the drop across this, then I can get the Vs. So Vs is equal to VR plus drop across this drop across this series impedance is nothing but Is into Z. So I can write down this expression, Vs is equal to VR plus Z into Is. But I know that what is Is? Is is equal to IR plus IC. Put the value of this IR into IC and simplified it, you will get the expression of Vs here. So what we require, I already told that our objective is to find out the equations of the sending end voltage and equation of the sending end current in terms of receiving end voltage and receiving end current. So we already got these two equations, and I can write this in matrix form. So Vs is equal to 1 plus 5z z y into 1. So if you expand this equation, you will get Vs is equal to 1 plus yz into VR plus z into IR from this equation, and Is is equal to, you can write it from these expressions. So from this ABCD parameters, A is equal to, this is my A, this is my B, this is my C, and this is my D. So if in exam if it is given that derive the ABCD parameter for medium transmission line with N condenser method, and then you need to derive up to this point. The weightage for this question is around 3 to 4 marks. 3 to 4 marks. Now based on this, we need to draw the phasor diagram. Now I will explain that how can I draw this phasor diagram. For that, drawing of the phasor diagram is quite easy. For any phasor diagram, you need to start with some reference phasor. For this entire chapter, generally we will take the receiving end voltage as a reference phasor. So I will take this receiving end voltage, that is VR, as a reference phasor. That angle 0 gives the indication that it is a reference phasor. So I will draw first this VR. Second thing, I will draw the current, receiving end current IR. Now you can see that the receiving end current IR is, the magnitude is IR and angle is minus phi. This minus phi is nothing but the power factor angle of the load, and in this example we have considered that the power factor of the load is 0.8 lagging. So I will draw this current IR with in lagging positions with respect to receiving end voltage VR. So I will draw this first. After drawing the reference phasor VR, I will draw the receiving end current IR at an angle phi. Now this is receiving end current we have already drawn. Another current we have, this is IC. Then IC is a charging current, and this current is drawn by the capacitance. And you know that the capacitance current always leads the voltage. In this case, the current IC will be drawn at 90 degree leading with respect to VR. So in this way you can draw the phasors for the charging current IC, and once you draw these phasors for the charging current IC, you have this equation that IS is equal to IC plus IR. The phasor sum of IR and IC will give you the current IS. This current IS, look at this current IS flows through this series impedance. Once this current flows through the series impedance, it will cause the voltage drop. The series impedance is divided into the real part and imaginary part. This current, when it flows through the resistance, it will create a voltage drop of IS into R, and when this current IS flows through the XL, it will cause the voltage drop of IS into XL. I will draw this IS into R drop is in phase with IS. If you look at the orientation of this IS and orientation of IS into R drop, they will have the same angle of lagging, because the drop across the resistance is always in phase with the current. So IS into R drop, this phasor, IS into R phasor, is in same directions of the IS. Again, you know that the drop across the inductive reactance is at 90 degree compared to IS into R drop. I will draw this one, another drop, that IS into XL. The phasor sum of IS into IR and IS into XL gives you the IS into Z. We have one more equation, that Vs is equal to VR plus IS into R plus IS into XL. So that phasor sum of this VR, IS into R, IS into XL, which will give me this entire value of sending end voltage. This sending end voltage can be obtained in this way. Displacement between receiving end voltage and sending end voltage is given by angle delta, that is phase angle delta. I hope that you have understood this. Now let us discuss or derive the ABCD parameters for medium transmission line with type 2, that is pi model representation. In this pi model representations, the total shunt admittance of the line, we already calculated this shunt admittance of the line Y. In case of the pi model, what we will do, the entire shunt admittance of the line will be divided into two parts. That means one part is Y by 2 and another part is Y by 2. So this half of the shunt admittance Y by 2 is considered to be lumped at the sending end, whereas the other half of the shunt admittance Y by 2 is considered to be lumped at the receiving end. If you refer this figure, then in this figure I have shown it, this half of the shunt admittance to ground, this Y by 2, this Y by 2 is considered at the receiving end, whereas another Y by 2 is considered as a sending end. Voltage across this Y by 2 is Vs and voltage across this Y by 2 is Vr, because we consider this as connected at, we consider this Y by 2 lumped at the receiving end, so voltage across this is Vr, and for this the voltage across Y by 2 is Vs. This is a simple thing that you need to consider. Based on that, now we will start derivations of ABCD parameters. So these are all the equations for ABCD parameters for the pi model representations. So it starts with first equation, that Vs. You can see that this is my Vs. Vs is available here, right? This Vs is nothing but the summation of the two voltages. One voltage is this Vr plus voltage drop across this impedance Z. Now you look at this, the current flowing through this impedance is Iz. Hence that Vs is written as Vs is equal to Vr plus Z into Iz. This is my equation number 1. Also you can observe that this Iz, this current Iz, if I apply the KCL here, then this Iz is divided into two currents. That one current is IR and another current is IC2. Hence I can write the expression of Iz is equal to IC2 plus IR. Now IC2, again I am repeating that IC, that is a charging current, and it can be found with the expression IC is equal to Y into V. So Y is equal to Y by 2, because this is magnitude of this is Y by 2. I will take it as a Y by 2 and the voltage applied across it is VR, because this is connected across VR. So IC2 is represented by this component. Hence Iz is equal to, this is my expression of Iz. Now use equation 2 in equation number 1. That means I will use this Iz in equation number 1. By putting this, I will get the equation of Vs, and this Vs is obtained in terms of the Vr and Ir. That was my objective to get. My objective is to represent sending end voltage in terms of receiving end voltage and receiving end current, and equation 3 gives that same relation. My another objective is to represent this sending end voltage in sending end current in terms of receiving end current and receiving end voltage. But this relation will not give me any value of the receiving end voltage or receiving end current. So I need to convert, I need to modify these equations. Use equation number 2 in above equations and simplify that. You will get this Is in terms of Vr and Ir. That was the objective of these derivations. So we got equation number 3. You get the sending end voltage in terms of the Vr and Ir, and the sending end current Is is also in terms of the Vr and Ir. Just make it correct. This is equation number 4, not equation number 3. So this is the summary of these ABCD parameters of medium transmission line, and you can identify that the A, B and C and D from these matrix equations. Now it's time to draw the phasor, right? So in this way you can obtain the phasor diagram for the medium transmission line in pi configurations. This is my third representations of the medium transmission line. This is a T model network. In T model network, total shunt admittance Y is considered at the center of the line, whereas in this case we will divide the series impedance into two parts. Z by 2 and Z by 2. The first half part Z by 2 is considered from sending end to the middle of the line, and another Z by 2 is considered from middle of the line to the end of the line. That has been represented here. The entire shunt admittance of the line is considered at the middle of the line. That means this is Y is equal to J 2 pi Fc is considered at the middle of the line, and voltage across this capacitance is considered as Vc. So based on this, we will derive the ABCD parameters of this line. You know that this is my Vc. Vc is nothing but the voltage available across this capacitance, and this is my one loop. In this one loop, you can see that there are two voltages, one voltage drop across this and another is voltage VR. So VR plus Z by 2 into IR, this is my equation number 1. Again, you can see that this is my current IS. This current IS is divided into IC1 and IR. I can write this equation. Then IC is modified with this Y into Vc. This is my equation number 2. Use 1 in 2, you will get equation number 3. And this is my objective to get sending end current in terms of the VR and in terms of IR. This is my sending end voltage Vs. This is another loop. In this my another loop, this is Vs, voltage drop across this Z by 2 and Vc. The Z by 2 into Is plus Vc make the use of Vc from 1 and Is from 3. Simplified it, you will get Vs is equal to in Vs in terms of the VR and IR. This is the summary. From this you can derive the ABCD parameters and you can identify it. This is the last slide. From this we can draw the phasor diagram for the medium transmission line in T configurations. It starts with VR, then draw the receiving end current IR, then this is IC. The summation of IR and IC gives me the IS. Now important to look at here. First, from VR I will write the expression of V1 because this is my VR. From this VR I will write the expression of V1, and after writing the expression of V1 I will write the expression of Vs. So you know that this V1 is nothing but the VR plus voltage drop across this and voltage drop across this. So I can write the expression of this V1 is equal to VR plus voltage drop. This is voltage drop across resistance, that is in phase with IR. That is remember that this is not in phase with IS. This IR into R by 2 is in phase with IR, and this is 90 degree. This is 90 degree. This is IR into XL by 2. So phasor sum of this my VR IR into R by 2 and IR into XL by 2 gives me V1. Look at this another loop. In this another loop I want to write down the expression of Vs. Vs is nothing but the summation of V1 plus voltage drop across this and voltage drop across this. So this is my V1. The current flowing through this element R by 2 is Is. So this Is into R by 2 is in phase with Is. This is Is into R by 2, and the drop across inductive reactance is 90 degree ahead of this. So it will be Is into XL by 2. So this is V1. This is another. This is third one. So finally I will get this Vs. Angle between this Vs and this VR is phase angle delta. So in examinations the questions may be derive the ABCD parameters and draw the phasor diagrams for the medium transmission line for all the configurations. If the questions will have all the configurations, then it may be of 10 marks. But if I will ask in breakup that derive the ABCD parameters for medium transmission line for type 1, then it may be 3 to 4, then For the pi it may be 5, and for the t it may be 5. So accordingly you need to prepare and you need to write your answer. I hope that you have understood this derivation of ABCD parameters of the medium transmission line, and you know that how to draw the phasor diagram. To draw the phasor diagram, you just need to understand the equations. If you understand the equation, then you can easily draw the phasor diagram. For any questions or for any query, you can write to me on email, or you can ask the question through the LMS platform also. Okay, thank you.